free body diagram, right? Free body diagrams. So in free body diagram, a sketch or diagram of a part isolated from the mechanism in order to determine the nature of the forces acting on it. Right. So this is how we draw a free body diagram. Say I will show an example. So if I have a 4-bar mechanism like this, so this is our 4-bar mechanism, right? So this link is grounded. So here is a joint, here is a joint, here is a joint, and here is a joint, right? So according to this sentence, diagram of a part isolated from the mechanism. So if I ask about something about this point, right, whether will it be in equilibrium or not this point, this link, so I will keep this as A, this as B, this as C. So if I ask you about something about the equilibrium of B point, what you have to do is you need to break that B and you need to isolate it, right? Isolate this B point. So you know this is a pin joint, this is also a pin joint, right? So when you break a pin joint, right, if this body is in equilibrium, right, if the body B is in equilibrium, there's a joint, actually there was a joint, right? But when I break this joint, there's no joint now. But what would be there? There will be two forces, right? There will be two forces. So usually we denote those two forces as vertical force and horizontal force, right? Similar way about this point also, right? Since I broke this one, I will have two forces acting on it. So assuming this is in equilibrium, what would I do? I will draw a horizontal and a vertical point, a vertical line, right? Force member. So this is our horizontal force member, and this is our vertical force member. Why are we actually doing this? So here, if you see, I have arbitrarily take a vertical and a horizontal direction. It need not this vertical should go up and this vertical should come down. It is not like that. You can draw arbitrarily. If it is given equilibrium, then if you draw one force member upwards in a link, then the other force member automatically will be acting opposite to it. So if you combine this vertical and that vertical, this will, right? So if you combine, this is going upwards and that is coming downwards. So that will be in equilibrium. Similar way about the horizontal force also, right? So if you combine these two horizontal forces, this horizontal force is acting this way and this horizontal force is acting that way. So they are opposite to each other, right? They are opposite to each other. So which will form a equilibrium member. So if it is given, then usually we break that particular link and draw like this, right? So only for the pin joint, this thing is applicable whether to have H and V alone, right? So we'll see a sketch or diagram of part isolated from the mechanism, right? So this is our 4-bar mechanism. Now I remove this part to make it isolated in order to determine the nature of the forces acting on it, right? Allow us to reduce a complex mechanical system into smaller, more manageable pieces. So if you given about this big diagram and asked you to determine, so this would be easy when you do, right? So since we can't determine forces in these 2 points, right? So I will say y, but this one and this one and this one we can decide, right? So in each point, what we do, if there is any relative resultant force, right, then this link will not be like this, right? Because if there is a force, then either it should move or it should break or something it should do. So since nothing is happening, I will assume this F is a 0. So I told you, while breaking each joint, we will have a vertical as well as horizontal component, right? So for this one, I will arbitrarily put this as F horizontal and this as F vertical. So in this link, right, in this link, this is F horizontal and this is F vertical. So in this link, this would be F vertical and this would be F horizontal. So when you add this link and this link, this FV and this FV will be equalized to 0, and this FH and this FH will be equalized to 0, then there will be 0. So that is this 0, right? Right. So if I have FH this way in this link, on the other end, I will have FH on the opposite direction. And since here I have FV in the downward direction in this link, I will have in the upward direction, right? That vertical. Similarly, for this link, since FH is in this direction, I will have FH in this direction and FV in downward direction, right? So if you adjoin these two, here is an FV, here is an FV, that is 0. Here is an FH, here is an FH, that is 0. So resultant is 0, right? So this is how we draw the free body diagram. So this is what called as the free body diagram. So we make all individual links as a separate link, right? The forces applied to the FBD, so FBD is a free body diagram, can then be summed to provide an equivalent for the piece. So now if you join all the vertical forces, right? So I have FV, FV, 2FV, FV, FV, 2FV. So upward 2FV, downward 2FV, 0. FH, FH, 2FH this way, FH, FH, 2FH this way. So FH and FH will be 0. So there is no net force, right? So this is to make the system easy to solve the forces, right? Then we can use these equations later to solve the problems. So now we'll see what are the advantages of free body diagrams. They make it easy for one to translate the words and thoughts and ideas into physical models, right? So if we draw a diagram, right, a physical diagram, right, there we can mention like all the parameters which are given, maybe the length or the force or any distance, mass, anything, any data we can draw in the diagram, right? So usually it is stated that like 100 words can be denoted by a diagram, right? So this is why we draw free body diagram in order to denote all the parameters, right? So if you want to do a numerical, it's better if it is in a diagram, right? Rather than in a words, right? Rather than in words, then if we can translate the words into the diagram, that will be easy. They assist in seeing and understanding all facts of a problem, right? So if we note all the parameters in a diagram, then we would understand, did we miss any parameters, right? So in that case, if we missed any parameters, then we can note them in the diagram, right? So they assist in seeing and understanding all facts of the problem, right? Then they help in planning the attack on the problem. So then we can imagine from where to start. So if we denote everything in the diagram, then we can assume, we can understand where are the forces acting, which are the line of forces and where are they passing through. So in that case, we can go to a particular start from where to start, right? So this is help in planning the attack on the problem. So where to start the problem? Either we can start from the force or from the momentum, right? So based on these diagrams, we can start or we can guess where to start from, right? Then they make mathematical relations easier to see and find. So when we dissolve the forces into horizontal and vertical directions, it is easy if we have it in the diagram, right? So forces won't act always either in horizontal or in vertical position. They may act in angles also. So when we are dividing it into horizontal or vertical, it is easy if we have it in the diagram, right? Then the methods used in the solution may be stored to future references, right? So we can study easily if we have these things in a photo. Because so this is why we have this free body diagrams also, in order to solve the problems easily, right? So these are few advantages of free body diagram, right? Few advantages of free body diagram. So these are number of forces acting on this particular body, right? This particular body. So here is the mass. This is a normal reaction. This is the frictional force, and the mass we divided into horizontal and vertical axis, right? So this is the actual forces acting on this particular body, right? So our free body diagram is also something like that. So particular lines. So in this diagram also, here is one force acting this way. There is a momentum, and there is another force in this pin joint, right? So if we remove this rod from this pin joint, so here I have a force F1, here I have a momentum T. Since I break this one, I will have F2 in both directions, horizontal and vertical. But since this F2 is acting horizontally, we will not have any vertical component. If it is acting in some angle, then I will have both vertical and horizontal component. But since this force is acting horizontally, I have only horizontal force and there is no vertical force. So I remove this rod alone from the pin joint, right? From the pin joint, to make it as a free body. So free body by the name means the body free from all these joints and all, right? So we take that body alone and mention all the forces in order to find the solution, right? So this is what meant by free bodies, right? So here we have an activity, right? Draw the free body diagrams for the following two-dimensional analysis. So free body diagram we draw only for the body, right? Not the surface or plane or whatever it is supporting, right? So if you assume this case, right, this is some kind of support, and this is also some kind of support, but this is a cable, right? This is a cable. In this case, this is a surface, this is an object, right? Here also this is a surface and this is an object, right? So in these cases, we will denote the forces only for the object and not for the surface, right? Because we are going to do all the calculation parts only in the object, not for the surface, right? Because in the friction diagram also, we are doing just for the purpose of the body which is being sliding, right? So if there's a body, we are doing calculation only for this body and not for this plane, right? So this plane will always stable, but this body, it can move downwards. So if I'm applying some force, it can move upwards, right? And it will have like certain forces, right? So everything we are denoting in order to find the movement of the particular body and not for the plane, right? So similar case is applicable for these cases also, right? So since this is a surface, this is a surface, this is a support, we don't mention forces on the support because we don't need them, right? We don't need them. So whatever we need, that part we will do, right? So if I want to draw this particular diagram as a free body diagram, then I have a body like this, right? And it will have a mass, okay? It will have a normal reaction. If it is moving downwards, it will have a frictional force, right? That's all, right? So this is frictional force, this is mass or weight, and this is normal reaction. So this is what called as the free body diagram. So we take that particular object outside and denote only the forces available on that particular object. We call it as free body diagram. So in the case of this diagram, right, weight of the cable is negligible, it is given. So this cable does not have any weight. Okay. So I told you, when we draw this free body diagram, we take that particular object out and then draw the free body diagram, right? I take this cable out, right? Now this cable has two joints, one here and one here, right? So there are two joints. If it is a pin joint, right, this is a pin joint, right? Because this will move here and there, right? As like a connecting rod of the piston, right? So if we break a pin joint, break in the sense, if I am taking this section alone, leaving this and this part, okay, at that time, that pin joint will have two forces, one on the horizontal direction and the other one on the vertical direction, right? One horizontal and one vertical, right? So whenever you break a pin joint, that will have two forces, one on the horizontal and one on the vertical direction, right? In this rod, right, if it is to be in equilibrium, right, if this rod is to be in equilibrium, we must have balanced forces, right? So here, if it is acting upwards V, usually we put downwards V on the other end, right? Similarly, if this is acting this way, right, positive x direction, then on the other end, we will put an H which is acting on the negative direction, right? So if you see, right, this H is in minus x direction and this H is in plus x direction, so they would be removed, right? Similarly, this V in the upward direction and this V in the downward direction, so that will be removed, right? So altogether the resultant force would be 0. Since this is in equilibrium and this does not have any weight, right? This is 0. And here we mentioned weight of cable is not negligible, right? So weight of cable is not negligible, which means the cable also have some weight. In that case, right, we will have a downward force, which is the mass of the cable. We write it as weight or mg, right? So this is the free body diagram for this cable with mass. And if it is without mass, then we will not have this component. We will have only these components, okay? Right, so this is the free body diagram for this particular figure, right? So this is a surface, okay, that's a smooth surface, fine. And this can be considered maybe a roll type object or cylinder or whatever it is. So in smooth curved surface, right, in curved surface, the normal force will be acting always perpendicular to the surface, right? The normal force will act always perpendicular to the surface. So this force is okay. This is correct, right? N is okay. When you see the mass, right, mg, you should understand gravity is always applied downwards, not in some angle, right? So here the mg will be applied directly downward, right? So it will not be applying in some angle or perpendicular to this, right? So when you make this mg, then we will separate it as this way mg cos theta and this way mg sin theta or whatever it is based on the angle, right? So for example, I will write this can be mg cos theta and this way it would be mg sin theta, right? It can be based on the angle, right? Just for the sake of mentioning, I am writing now. So mg will be applying only on the downwards direction. You need to understand that mg will not act on any angle, right? That will always act downwards. But when you split it into horizontal and vertical parts, that will have some cos angle here and sine angle here, or maybe sine angle here and cos angle there, right? So n is correct and mg will always act perpendicularly. So when you split it, then mg cos theta will be applying perpendicular to this, and mg sin theta will be applying on this plane, right? And we will now go for the roller support, right? Roller support, yeah, this is okay, correct. So the normal force applied will be on this direction, and the weight of this one will be acting downwards, right? That is mg. But only thing is, you need to draw those forces exactly on the point, right? So on the point. So if this is the point of contact, then the normal force would be perpendicular to the surface of contact, and mg will be directly downwards, right? So the two forces are correct, but you need to draw them on the particular point. This can also be considered as a pin joint, right? So here what we need to do is, here we have two objects, right? So this is one object and this is another object. Okay, this is the plane, so that part we don't need. So when we are drawing for a free body diagram for a particular body, then we will split it like this. If we are drawing for a system, we will keep as it is and then we will draw, right? So here, yeah, normal force is this way, that is fine. It may have some weight, that's also fine. So if I consider this as moving this way, then there will be frictional force on the other side, that will also correct, right? So is it is, if I apply the free body diagram for this whole system, right? If I apply for the whole system, if I apply for the particular body, right, this body, so this will have some weight, okay, and there will be a normal reaction from the ground, right? So this is normal reaction and this is weight, and if it is moving that way, there will be a friction this way, frictional force. And since I am applying some force this way, there will be a force. These four forces will be applying on this round body, and this one, so this can have a weight not mentioned. If it is, then we need to mention, right? Yeah, and here if I ask this is a pin joint, then I told you here in this condition, there is, if it is a pin joint, then there will be two forces. One is on the vertical and the other one on the horizontal sides, right? Maybe if I am pushing this one, there will be a force applied this way if I am pushing it. So since we have this horizontal and vertical component in the rod, we will have equal and opposite horizontal and vertical force here also, right? So here the vertical is going upwards, so there I will put the V as downwards, right? And here the horizontal is applying this way, so there I will put the horizontal one this way. So this is somewhat important. You see, when you add this system and this system, you will get this system. Is that okay? When you add this figure, right, that's a free body, and this figure, that's also a free body. When you add this and this, you will obtain this system. Is that okay? In this system, right, in this particular system, you have one normal force, right? One normal force and one mass or weight and one frictional force, and there can be one force applied by the rider, right? So there are 1, 2, 3 and 4 forces, right? When you combine these two and make this as this system, again you need to have only those 4 forces, right? So that is force applied if it is mass or weight, normal, right, normal reaction, and frictional force. Only these 4 should come. This V and this V should be cancelled out, right? Also this H and this H should be cancelled out. They are equal. Just for the purpose of finding the force or momentum or any numerical value of this system, if we break it for our purpose, then they are equal in magnitude. Otherwise, if this V and this V are different, what will happen? Can somebody say? If this V is 50 and this V is 70, then what will happen? If first we will draw this diagram for the system, right? Based on the question. So if this system diagram is enough, then we will stop with that. Maybe in the system, if we want to find something, like if I ask, okay, what is this V in case, right? What is this V? If I ask, then you need to break this diagram into this diagram. If I ask only about Engr.JOY, then you don't need to break the system into free body diagram. If it's enough if you apply the equations only to this whole diagram, right? So if it is necessary only, you need to break this into free body diagrams. If it is not necessary, it is enough to stop with this and find the value, right? So this is also correct, this is also correct. So what I'm doing is, if I need to find the V, I need to go for this, because here I don't have a V now. I don't have any V here. So if I want a V, then I need to break this one into these two and obtain a V, right? So this is why I break it, okay? So if this and this are different, then this cannot be a system. How come we fix this one? We can't fix it, like either it would be breaking. So if there's another one force acting this way, that is 50, and this is different, then that is actually broken part, right? That's not a system. So if that's a system, then that must be similar. So that's why we break them into pieces which are equal in magnitude. So once we combine this and this V and this V should diminish, this H and this H should diminish, and it should bring a system like this. So similar case for this also. So if I am applying some force here, that force will be there, right? So if it is moving this way, then there will be a frictional force, right? I'll denote it as F. And then there will be a weight, right? At mg, and there will be a normal reaction, right? So on this normal reaction part, right? This normal reaction, if the surface is a curved surface, right? If the surface is a curved surface, or the object is curved in surface, then the normal force would be perpendicular to the surface of that touching point, right? So here object also a curved object, plane is also a curved plane, right? So in that case, the normal force will be applied perpendicular to the point where these two touch each other, right? So here also the same case. So this is a curved surface, this is a plane. So I draw a perpendicular to the curve, and the normal force will be applying on the perpendicular direction. So similar case here also, right? So if it is a curved surface, then I draw a perpendicular, normal force will be applied perpendicular to that, right? But here the case is different. So here we have three wheels, so there will be three forces, right? There will be three forces. So if it is asked to find force on each wheel, then you need to mention three forces. If it is asked only to find the normal force, then it's enough only to draw one normal, right? Okay, so here I have free diagrams, some more, right? Some more diagrams, right? So what is shown in this figure is just a joint, right? So this is not an object. So probably this will not have any mass, right? If it is an object which is fixed, maybe a roller or something, then we will have. So this is just a pin connection. You see the topic, it is only a pin connection, right? So a pin connection will not have any mass. If there is no mass, then there will not be any normal force, right? This is just a pin connection, right? So in that case, it will have only horizontal and vertical force on the object and the pin. So usually we will not denote that, right? So the forces which are acting on the pin, we will not denote, but on the object, we will denote, right? Okay, built-in support. So built-in support, okay, this way force is correct, and this way also correct, and that will have a bending moment also. So and then there I have the gravitational acceleration. So I told you gravitational acceleration will always be in the downwards direction. So there are no surface, right? So we don't know whether it is flying or it is in the earth or what it's doing. So there will be only downward force, that is mg, that is fine. And for the spring action, right? there's applied a force F. Okay, so F is equal to Ks, it's mentioned, so there's a force F, that's fine. So there will be a reaction, that reaction is also fine, but only thing is, for the spring joints, reaction we will not mention as R, the reaction we will mention as, sorry, not mention as N, we will mention as R. N is usually used if there is a normal reaction from a surface and probably with the mass, right? So usually, right, usually I'm saying this would be the case, but if you write N here, that's not wrong, right? But what I'm saying is usually we denote this like this. In case of spring, we will have a force F, and then the reaction force would be denoted as R, right? So here he gave two diagrams, right? Linear and non-linear, right? Do you think these graphs are given for certain purpose or any information regarding this diagram? This is given for a purpose. Otherwise, they could have just give only this diagram, right? They don't need to give this one. So they gave this one for a purpose. So here, if you see, that is linear force, right? So F is equal to Kx, it is abiding that F is equal to Ks principle. So in that case, F will be equal to R, that is fine. But here, right, if you see, there is non-linear hardening or softening, right? So if this is too soft, right, what will happen? This will start to extend due to the excess force. Since it is not linear, when you remove that force, it will not come to this level, right? It will not come to this level. It may have stopped with somewhere here due to its elasticity, right? So that is why this diagram is given. So in such a case, the F would be greater than the R, right? Okay, so this is actually material property. So in case if you are applying a force which is greater than this particular formula, right, F is equal to Kx, then it will not come back to the initial position, which is here, but it would stop with somewhere here, right? So that's why these two graphs are given. You see, it is sliding some guide. So this one will slide here and there. So you need to assume this one as just a joint, right? You don't need to take any mass unless it is given. So this mass will not be there, right? So this sliding joint, yeah. So it can have friction or not. Okay, that's fine. And there's a joint. So this and these forces are okay, right? This and okay. It can have a friction, but it will not have any mass unless it is given. It does have some mass, right? So this table will give you a brief of whatever you have done so far, right? The previous last two slides, right? So we'll see one by one, right? So this one is a cable. So the first diagram we draw, right? So you see cable part is drawn, right? So since it is hang on this cable will have only force directed on that particular direction. So if you know the theta, then you can write it as F cos theta, and on this way the F sin theta. So when you try to solve the problem, it would be easy, right? So there is only one force. If nothing talked about mass, then we don't need to worry about the mass. Okay. And here I have the cable, sorry, not cable, roller, right? So in roller, the force will be always perpendicular to the surface of that object, right? Always perpendicular to the surface of the object, and there will not be any horizontal force on the roller joint, right? You need to, so this part anyhow you need to understand, right? If it is a roller joint, then there will not be any horizontal component of the force. The force will always be perpendicular. And then I have smooth support, right? So it said smooth support, so there is no friction force. So I told you, if there is a curved surface, right? If there's a curved surface, then the force will be perpendicular to that surface, right? So if there's a curved surface, then perpendicular to that surface, we will have the force, right? So if the angle is known, then we can put the angle theta. So when you dissolve it into two directions, so this would be F cos theta, and the other direction will be F sin theta. So this will be F sin theta. So only if it is mentioned, it's smooth support. If there is any friction, then whether it will move downwards, then we will have friction upward. If it is moving upward, we will have friction downwards, right? And then external pin or pin joint, right? So this is what the sixth diagram was, right? That's just a pin joint. So if there is a pin joint, and if there is nothing talked about the mass, we don't need to worry about the mass, but we will dissolve the forces into horizontal as well as vertical direction, right? Either you can use HOV or you can write Fy direction and Fx direction, right? Two unknown forces, Fx and Fy, right? So this is pin joint, external pin. And this is also a pin, that is internal pin. So this is actually between two links, right? So this is also a bar, this is also a bar. This can be a link, but here if you see, that is the start of the joint, right? So that is fixed with the plane. Here it is fixed in the link, right? So that's why it is external pin and this is internal pin, but the force is same, right? So one horizontal and one vertical, right? And if I have a fixed support, so in that case I will have Fx, Fy as well as a momentum, right? So you can consider this as a pin, but a fixed pin, right? So this will have a momentum also, right? Momentum also. So there will be three unknown. Fy vertical is unknown, Fx horizontal is unknown, and the momentum M is unknown, right? So there will be three unknowns. So these are the diagrams, right? Connection diagrams, and these are the reaction free body diagram. So if you see in the free body diagram, we will have only the body which is considered, right? So if I take this diagram, here I have a plane, and the plane it is fixed, right? So I will not draw the plane or connection, I will draw only the body which I need to calculate, right? So here both are bodies. So if it is asked to calculate on this body, then I will draw only for that body. Or if it is asked to calculate for this body, then I will draw only for this body. So if it is Fy, then I will have Fy here. If this is Fx, then I will have Fx on the other side, right? So while joining this joint and this joint, these should diminish and it should be like this, right? So this is a smooth support. So this can be a plane and this is a rod kept on that, right? I'm not going to worry about this plane, right? I will draw only for this object which we consider, right? So similar way here, there's a roller support. So roller, I'm not going to worry about. There's a plane that I don't care, right? I need only for this object and what's the force on that. So I will draw only that particular object, right? That particular object. So similar way here. So I am not going to worry about the wall, but I will draw the cable and the connection. So if you want, even you can break here. You can remove the cable separately and the rod separately if it is asked, right? So this is why it is called free body diagram. So we will consider only about the body and not about the supports. It can either be a wall or a plane or slant plane or roller or some joints. We are not going to bother about that. We will just draw only the body and the forces acting on that particular body, right? So now we will go to the procedure. What will we do if we find a question, right? Procedure of analysis: support reactions, free body diagrams, equations of equilibrium, right? So if the question is given in a written format, right? So first we will draw a diagram, then we'll support it with the reactions and forces and everything, right, to the system. Then if it is asked to find the forces acting on a particular body, then we will make that body particular, or we'll make that body separate and we will apply all the forces on that body. Then we will solve it for the equilibrium equation. So we have only 3 equations, right? One, sum of forces in the x direction is 0. Then y sum of forces in the y direction is 0. And then the momentum about any arbitrary point is 0, right? So we will apply these 3 equations and we will find the answer, right? So the question will be given in a written format. Sometimes there can be diagrams, doesn't matter. If we don't have the diagrams, we can draw the diagram. Then apply all the forces and length and whatever the data given. Then draw the free body diagram if it is asked on a particular body. Then use your equations and solve it, right? Then we will go for an example now. So this is a question, right? We'll start from the simple question and then we'll go deep. A bar of length 3 meter, right? So this is a bar, length is 3 meter, right? Is given. On equilibrium of 2 supports labeled A and B. So 2 support A and B, right? 2 supports are there. The mass of the bar is 20 kilogram, right? So mass of this bar is 20 kilogram. Determine the forces exerted by the 2 supports, right? So in this question, the question is also given, the drawing also given. Even if there is no drawing, you can draw a drawing, right? Total forces in the horizontal direction. So here we don't have any horizontal forces, then we don't need to use that. And then total forces in the vertical direction, sigma y equal to 0. So we will apply that one. So on the upward direction, we have FA, right? That is one force. And also I have another force FB that is also acting on the upward direction. And I have a force downward direction minus 200 equal to 0, right? So this is one equation. Then I can take momentum of any arbitrary point, right? Momentum of any arbitrary point, right? So you can take about A, or you can take about this midpoint, or you can take about this B, right? So starting from M, I will write. So this, I will take moment, you see here on the clockwise direction, right? So if I see clockwise direction, this force is clockwise, right? So that is 1.5 meter into this force FA, right? So about M, 1.5 into FA. And when I come this way, this is anti-clockwise direction. So I will put minus, right? And this distance is, so total is 3 meter and 1 meter here. So which means this much is 2 meter. And I have 1.5 meter here. So which means here it is 0.5 meter. So minus FB into 0.5. This is my second equation. Okay. Anybody who want to say I can take from either A or B? So yeah, if I take from A, right? Again, so if I'm taking from A, this will not come. I'm taking clockwise direction. So I have 200 Newton into 1.5 meter here. And there is another force that is actually opposite, right? My motion is clockwise, but this is anti-clockwise. So I will write minus force FB into direction length 2 meter, right? FB into, that will be my second equation. Okay, so we'll try from B also, right? So if I'm taking from B, right, I'm taking clockwise, right? So FA into this length 2, and here I have mass acting downward, so that is also in the clockwise direction. No, that is in the anti-clockwise direction, right? So I will put minus 200 into this length 0.5, right? Will be equal to 0, right? So that's also second equation. So you can take moment about any arbitrary point. You can take from A, or you can take from M, or you can take from B. But okay, so now can somebody tell me which of these three would be easy to solve? A, B, or M? So here we have three spectacular points. A is there where Fa is acting. M is there where the mass is acting. B is there where force B is acting. So these are the three spectacular points. Or if you wish, you can just point the point C here, right? Maybe like 0.75 meter from here, and you can take from that point also. That's your wish, right? Doesn't matter. So since I am given with three specific points, I am going to try those points. If you wish, you can take any arbitrary point anywhere on this bar, right? It can be here or here or here or even here, it's fine, right? Now we will see about B, right? We don't need to write all three equations. Any one equation is fine. I'm just writing all three just for the sake of explanation to show you which one would be easy, right? So for B, I will take another color, right? So now I'm going to take momentum from B, right? So this is our B point, right? This is our B point, and taking momentum clockwise, right? Clockwise means this is clockwise, right? From here to here, this is clockwise. You know how a clock move, right? A clock will move like this, right? So this is clockwise. So from B, I will take clockwise motion, right? So which means it is moving like this. So if you see, FA is acting in clockwise direction, right? So that FA into the distance between A and B is 2 meters, right? So FA into 2. Then I have another force acting here, right? Another force acting here, right? So I have equation A, equation B, and equation M, right? So we'll see what will happen if I solve this one, right? So if I take this equation, right, first equation A, that is 200 into 1.5, that is equal to 300, right? Right, 300 minus 2FB is equal to 0. So 300 is equal to 2FB. Similar way, for B also, I will try to solve this one, right? FA into 2, right? So that is equal to 2FA minus 200 into 0.5 is equal to 0, right? So 200 into 0.5 is equal to 100. So 2FA is equal to 100, right? Then I will solve the third equation also, right? M 1.5 FA minus 0.5 FB is equal to 0. So that is equal to 1.5 FA is equal to 0.5 FB, right? 1.5 FA is equal to 0.5 FB. So this equation you can readily solve. If 2FB is equal to 300, then 1FB is equal to 150. This equation also, if 2A is equal to 100, 2FA is equal to 100, then 1FA is equal to 50. Okay. This equation, 1.5 FA is equal to 0.5 FB. So you just can sort it down. So you will get 3 FA is equal to FB, but you can't get an answer, right? So if 1.5 FA is equal to 0.5 FB, you can't get an answer. But it doesn't mean you can't get the answer. This equation and this equation you need to combine in order to get the answer. So you need to write one more step, right? But here, readily you got the answer, right? FB is equal to 150 or FA is equal to 50. So if you apply this equation here, right? So if FB is 150, then FA plus FB is 200, which means FA is 50. Similar way here, if FA is 50, then if you apply here in this equation, if FA and FB is 200, then FB should be 150, right? So either taking from A or B will be easy rather than taking from an M. Okay, so this is a scenario. So it is a kind of easiness, right? So you just can have it in your mind while you are sitting in the exam, or if you are lagging in time, right? You need to do it fast, right? So this is a kind of fast method, either taking from A or B. Why? Because if you take the momentum from A, OB, right? This is an unknown force, right? FA also you don't know, FB is also you don't know. So when you take momentum about A or B, the distance between the force and the point is 0. So which means if you're taking momentum about A, then the FA force will not come in the equation. You see, if you are taking a momentum of A, then FA force will not come in the equation. Similar way, if you are taking about B point, right? You see, B force will not come, right? Only A force is coming. But when you take a momentum of M, A is also coming, B is also coming. You don't know both A and B, right? So this is a guess. So when you take a momentum, try to start or take the momentum from an unknown force passing line, right? Unknown force passing line. Because this M you know, right? M you know. So it's better to have it in the equation. So here also I have that in the equation, right? M is equal to 200. I have it in the equation. Here also I have it in the equation. But here I don't have it in the equation, right? So this is a known body. It's better to have the known body in the equation, right? So whenever you are taking momentum, you take from the unknown force acting points, right? Right. So there is a question for you. So this question, this does not have a diagram, right? So first you need to read the question, then draw the diagram, apply the forces, right? If necessary, then break into free body, or if it is not necessary, then don't do that, right? And finally find the answer.